Okay, now let's progress with our regression examples. So here's an example that I want to work with. I'm going to say, look, let's imagine an experiment, not very creative on my part, but we're going to observe some birds after they hatch. We're going to measure their wingspan. Okay, so we might think about a hypothesis for this, which is sort of another way of saying our model. So some sort of model to describe wingspan growth. We would say the average. So we're not saying about so much any individual specific bird, but we're saying on average something would happen. The average wingspan increases with age, certainly at least over a certain time period. So that would be describing the slope of a line. A wingspan will be positive at birth. So we would have a positive intercept. Now, generally intercepts don't really have a meaning, but I am saying that in this case, it would have a meaning. Like the intercept would be our estimate of wingspan at birth, and then we were tracking it as the wingspan grows over days or weeks in the initial period of a bird's life. So you can then write down that linear model, and when I say linear, I don't mean that at this stage we have to assume that it will be a line. We could, require one of the log transformations on this. So the linear model just refers really to the method of estimation. The method of estimation is linear regardless of whether or not the shape is curvy. I know that's a pretty strange way of expressing things, but we can remember we can apply log transformations to the data. So at this stage of just writing down the model, we don't actually need everything to be linear. In this case, it turns out it is, but that's because I'm working with an initial example. So I would go and get some data. So we go and we measure wingspan, and we have birds of different ages. And you can see that we have, most days here, but we don't have a measurement on day 7. Maybe that was Sunday, for example, and so we didn't take a measurement on Sunday, and so on. So we've got different birds, different ages. We've got measurements on the wingspan. The question that we want to answer, so the way that we've framed the model, is to describe the average. So this is, sort of the general, on average, this is what happens. On average, it grows this much. Any given bird is going to have an individual growth pattern determined by the genetics. Some birds are going to grow faster than other birds, but on average, if you look at lots of birds, this is a general descriptor of the pattern. Okay, so what is the process that we use to fit a trend line to describe the average? So we create a scatter plot. So this is the scatter plot function, very easy function to use in R. You can see that the command or the function is the plot function, y tilde x. So length explained by age. And that makes sense, it's the way that we want to plot this. The thing that's being explained, or the dependent variable, is length. That's going to go on the vertical axis. Age is what does the explaining. That's going to go on the horizontal axis. So it's age in days, and it's wingspan in centimeters. We need to estimate the model. So it's the linear model. And so we have the LM function for the linear model. And if I can just bring this up, we've got a different color. Didn't know why that happened. So we've got LM for linear model. And this is our standard setup that we've used for functions here. ANOVA for the ANOVA function. All our tests, just LM. It's as simple as that. The dependent variable, the explanatory variable, and the name of our data set. So I haven't put with. The with command doesn't work anymore, but you just say the data set that I want to use, which is the data set I've read into R, wing.data. And what I'm doing here is I'm saving the output. So this is called the assignment operator. So I'm going to create in R an object called lmbird. Lmbird is going to be saving the results from my linear model. So my linear model that I want to fit to the data of dependent variable, which is bird wingspan length, and then the explanatory variable, which is bird age. And where is it going to find these variables? Where is R going to find these variables? It's going to find them in the data set. Now the coefficients are what you can use to get the intercept and the slope. So you call those the coefficient estimates. So what are they? They're your estimates of the intercept and the slope. So you can get them using the coefficient command. And when you want to add them to your plot, you use the AB line. So A is standing for the intercept, so it's AB line, a line with an intercept and a slope. And the magic thing about R is, because this is a linear model that we saved in lmbird, it can read directly the intercept and the slope coefficient from our object that we've saved. So we don't actually have to type in the intercept and the slope value. The reason that we do this is good scientific practice is about reproducibility and trying to minimize errors. So here we apply the function. So this is, really learning about fundamental skills in data science. We are going to run the function. We're going to save the output. We're not going to type it down or write it down. We're then going to apply our second function to our output from our first function, and that's going to plot our line. So at no point are we introducing the possibility that we might write down the wrong values. It's a really good way to be working. And then we need to add a legend to our plot. So when we have plots, we have this legend command. So this is there's a chapter on scatter plots in the course book, but you use the legend command. There are 4 options. There are 6 options actually. You can put the legend in the top left, top right, bottom left, bottom right, top or bottom. So they are the 4 locations around the page that you can put. And then you have to say what the legend is going to be. So we're going to have 2 things. We're going to have the observations, which are the observations for our data, and we're going to have a trend line. So you're going to get some practice at doing this, but all we've done is we've introduced a new function, the LM function. It's just like any other statistical test that you've been learning about, but what we're doing is instead of letting R print the data, we're going to save the data, and then once we save it, we can use it in different commands. And this is the command that adds a line, and this is the command that adds a legend to our plot. And these are the basic steps that you need to go through. So what do you get from that? You get something like this. So I have in my top left, you can see I have my legend that tells me the grey dots are a scatter plot of the actual data points. The black line is my trend line. So it's in my legend, my trend line. And you can see here I've got bird wingspan in centimeters. So I've got age going off here, and you can see these are not a perfect fit. So the important point here is remember, what is this line? How's this line been fitted? It's been fitted as the line that minimizes the sum of the vertical error terms. So what are they? These are all these vertical distances here that you can see. All right, so we've fitted this trend line to minimize the vertical errors. And that's what it looks like. And what does the trend line do? It describes what's happening on average. So it's not, the specific of any individual one bird, it's what happens on average. So if we look at the slope of this line, we have a linear model. So we didn't transform anything on the data. That's bird ages, or with an awesome looking typo. No typos over here. So we've got untransformed data. The slope of the line we find is 0.27. So we know from our generic understanding of the interpretation of this, we can say a 1 unit increase in Y results in, on average, a beta unit increase. So a 1 unit increase in X on average leads to a beta unit increase in Y. So a 1 unit increase or a 1 day increase, so an increase in time of 1 day results in an expected or an on average increase in wingspan of 0.27 centimeters. Now, the regression relationship, what we've got is, so what we've got here is not an explanation of the actual data, but of our fitted values. So this is a trend line, our fitted trend line. So what I've got here is our fitted value. Our trend line depends on our estimate of the intercept, our estimate of the slope, and our raw data. And these little hats, so we say y hat, so our predicted value. So our predicted value is what describes the average effect. Our predicted value depends on the estimate of the intercept and the slope. So our predicted wingspan, so it gets a little hat, is equal to the intercept. Our model generated an estimate for the intercept, and our slope, which was 0.27 centimeters, and age in days. So on average, this is what is being described. And mainly we're going to be talking about the intercept. Generally, actually, we're mainly going to be talking about the slope. Generally, we don't have any interest in the intercept. So this is our core thing. Now, the next thing that we want to know is, this is having our statistical testing. So could we get this value by chance? could the true value for the slope be 0 is really the question we want to know, what is the quality of our estimate of this 0.27? So we're going to be interested in questions of statistical significance. So we want to ask the question, is the slope estimate statistically different from 0? Okay, so we're very familiar with this kind of thing. That's sounding like a little bit like those single sample t-tests that we did. Is this something statistically different from 0, for example, particularly our paired t-tests, single sample type t-tests. So we're going to have exactly the same kind of t-test for our testing our slope. But before we do that, I want to just explain some intuition about our test. So when are we going to have good estimate precision, and when are we going to have poor estimate precision? And I think the easiest way to explain that is just with some illustrations. So what I've got here is two different types of data. So on my plot on the left, you can see that I've got a cluster of observations, or really what I'm saying is that my X values are quite clustered together. They're not very spread out. So what does this mean? It means it's hard to identify the correct trend line to fit to the data. And if it's hard to do that, we're going to be quite uncertain about what the true value of the slope is. Of course, if my data is nicely stretched out this way, so if I got a lot of variation in the X's, so a lot of variation in my data, it's much easier to fit a trend line and I get more precision. All right. So if there's more spread in the X variable, it will be easier to fit the trend line. And if it's easier to fit the trend line, I'm more certain about the true value of the slope. The other thing that I think that we can see is if I just have more data. So we've seen this one repeatedly, the value of more data. If I have a lot of data, it's easy to fit the trend line. I can be quite certain about it. But when I have very few data points, I am very uncertain about where the trend line is. So I'll be uncertain about the true value of the slope. In all of these diagrams, the reason I've put the sample means in there is because the trend line will always pass through the point of sample means. This is a mathematical property of the way that we estimate things. So our estimates will always, whatever we do, will pass through the point of the sample mean of the data. So before we go on to testing our statistical significance of the slope, what have we seen? We've seen that if we can reduce uncertainty, so in our t-testing that we saw before, the way that we were reducing uncertainty was to say, well, we could have growth chambers instead of growing things out in the field. We could reduce the variability in the data. Here, the way that we can reduce uncertainty is if the data on the x-axis is quite spread out. So if the data on the x-axis is spread out, it gives us more certainty. Or we could have more data. So they would be reducing uncertainty. If we reduce uncertainty, we have a better idea of where the slope is. If we have a good idea of where the slope is, then we're going to have more precise estimates and we're going to be more inclined to reject the null. Okay, and the null is going to be that the true slope is 0. And I guess what I'm highlighting here again, it's just at the end is same things are at play here. We're going to be going into doing statistical testing. So those same things about the type 1 and type 2 errors are going to be at play. And the way that we strike a balance between these different error types is by setting our alpha value at 0.05. And that's again what we're going to be using for this setup. So we're going to go on to testing the whether or not the slope is statistically different from 0. We're going to again require to set alpha at 0.05. Why are we setting alpha at 0.05? Because we have these competing type 1 and type 2 errors. And again, that's an opportune time for a break.